Okay, so the second part of chapter 1 starts with molecular orbital theory, and that is when atomic orbitals are mathematically combined to make new orbitals called molecular orbitals. So this is really multiple parts depending on how many atoms are in your molecule. But an atomic orbital deals with just one atom. The molecular orbital is dealing with the whole entire molecules. The lower energy molecular orbital is the bonding MO, and that is a result of those two individual waves coming together in constructive interference and getting a big wave, whereas the higher energy molecular orbital, or the antibonding MO, is the result of destructive interference. So that's going to form that node in there. So for every molecule, two of its molecular orbitals will be of interest for us, and that's going to be the highest energy orbital, or the highest occupied molecular orbital, or HOMO, and then we have the lowest orbital from among the unoccupied orbitals is called the LUMO, or the lowest unoccupied molecular orbital. This is the LUMO, and this is the HOMO. This is an atomic orbital here. This is also one. So those are two atomic orbitals coming together, and this middle section here is the molecular orbital. So we can think of two hydrogen atoms come together to form H2, and that is the whole molecular orbital. And those are mathematically combined together. So hybridized atomic orbitals, if we look at the electron configuration of carbon, so if you remember we drew that out in the last section, it had an electron configuration of 1s2, 2s2, and then 2p2. But the problem with this molecular orbitals is that we can see that there's only, according to this, two places to bind. So there's only two spots to bond. But we know, looking at methane, that it makes 4 bonds, right? So carbon is making 4 bonds, which we've seen already when we drew our Lewis structures, and that's been studied. So how do they account for getting these 4 bonds on carbon when there's only 2 spots in the molecular orbital? Well, they had to come up with a hybrid system. So we're going to get excited. Those electrons are going to get excited, and they're going to go get promoted from 2s to 2p. So this 2s electron here is going to get shifted up to here. So we can move that one to there, right? So we have 4 spots for bonding, right? Did we totally nailed it? Or maybe we didn't. So there's 4 spots for bonding, which is good. But if we look at methane, it's making 4 equal bonds and has equal bond angles. So these are all the same bond angles, and they're all the same types of bonds. So this is not representative of 3 2p orbitals and 1 2s orbitals. So there has to be a way to fix it. Well, what Pauling did was he hybridized the orbitals. He put the 2s and 3 2p orbitals together. He smushed them together. You can think of it that way. We have these 3 2p orbitals and 1 2s, so he hybridized it or smushed it together to get 4 degenerate orbitals. So we had 4 electrons. He put all these lines together and had an in-between level. So we have 1, 2, 3, 4 electrons, and they're all going to be this combined sp3. So all these atomic orbitals are now in equal energy to form 4 equal energy symmetrical CH bonds. So the hybridization that we're showing here does not represent a real physical process, but this is a mathematical explanation for how we see things bonding. So you'll see that this is an sp3 orbital. It has one big lobe in the front and this smaller back one. So this is built this way to get better orbital overlap. So what you can think of is these are the 3 2p orbitals. This is the 2s orbital. So s orbitals, if you remember, are round and spherical shaped. We have these 3 p orbitals that look like peanuts, and those get hybridized together to form these 4 individual lobes. And then we have, this is the sp3 here. Okay, so if you want to think of it another way, this is 3 cups of flour, 1 egg, and you whip those things together and it hybridizes to form you a pile of pancakes. So again, this is, I'm disclaiming here, this is an oversimplification of ingredients. You need more stuff than that to make pancakes, but maybe you get the idea here. So we have 3 individual bowls of flour, 1 egg, those get together and it forms something new. In this case of the sp3, you had 3 2p orbitals, 1 2s, they came together and made an sp3 baby. This is tetrahedral geometry. So all those bond angles are 109.5, and it came to be that way so that these orbitals are as far away from each other as possible. So all single bonds are sigma bonds. So this is CH4, and that is drawn out in the tetrahedral form. So you can see the S bonds here, the sigma bonds between the hydrogen and the carbon, sigma bonds between carbon to carbon here. So this is ethane, this is your sigma bond, and that is a face-on bond. So if you can pick up your hands and put your fists together, you're going to see that sigma bond. And there's lots of sigma bonds between carbon and hydrogen, and then carbon. So that is ethane, which is CH3, CH3. All of these are sigma bonds. Single bonds are sigma bonds. So we get a lot of orbital overlap between the S of the hydrogen and the sp3 of the carbon, or the sp3 of the two carbon atoms. For sp2, this orbital is not effective. We're going to hybridize these ones to make 3 bonds. So we hybridize, we get 3 sp2 orbitals, and then 1 2p, and that's going to form your double bond. So sp2 hybridized carbons have 3 equal energy sp2 orbitals and 1 unhybridized p orbital. So it can form 3 sigma bonds, and then there's 1 pi bond. P orbitals overlap with each other and form a pi bond. These are sigma, and notice the bond angle is different here. It's a little bit wider, but again, it still is as far apart from each other as possible. So one of these double bonds is sigma, the second one is a pi bond. Okay, so ethene has planar geometry. So if we notice here, this is a flat molecule, which is why it's drawn on this slab. So it has planar geometry, and each of these atoms in ethene, the carbons, are sp2. So this is sp2, and this is sp2. It can still form sigma bonds with those hydrogens, and then we have 1 electron bond here. This is the pi bond. Unhybridized p orbitals in ethene form pi bonds, and then there's side-by-side overlap, giving both constructive and destructive interference. So what that's saying is that single bond here is a sigma bond. Again, you get that fist-to-fist bond, and then when you have that pi bond, it bonds side to side. If you think of 2 pregnant ladies trying to hold hands here or shake each other's hands, this first bond here, this is that head-on bond, this is the sigma bond, and this bond, or this handshake bond here, is the pi bond. So it's side to side. So that is the second bond that forms in that double bond. A triple bond is formed here, this is acetylene, by hybridizing the sp orbital. So just the s and the p carbon, and then there's 2 p orbitals here. So we have 2 degenerate sp orbitals and then 2 p orbitals. This is the triple bond. So one triple bond has 1 sigma bond and 2 pi bonds. We saw the 2 pi bonds here. 2p equals 2 pi. And then these are the sp. All right, so the sp atomic orbitals overlap, have that head-on to form the sigma bond, which is that first sigma bond. And then you have the 2 side-by-side p orbitals to form the p bonds. A triple bond has 1 sigma bond and 2 pi bonds. To note about hybrid orbitals, the first bond between any atoms always uses the hybrid orbital, except for hydrogen. Non-bonding pairs use hybrid orbitals, and then second or third bond between atoms use unhybrid p orbitals to form the pi bonds. So we want to look at the hybridization of each of these things. Single bonds are sigma and are sp3. Double bonds are pi bonds. Those are sp2. And triple bonds have 2 pi. Those are sp. For each of the carbons, these 2 are sp. And this is the structure of ibuprofen. There are no sp orbitals there. This is sp3. I'm just going to mark all the sp3s with this green here. So anywhere carbon is singly bonded, those are sp3. And then I'll use blue for the sp2. So double bonded carbons. This one is C double bond O. It's still sp2. these are sp2, these are all actually sp2 in this ring, and that is for all those. If we look at the properties now of the bond strength and bond length of carbon atoms for ethane, which is the single bond, this is sp3, that has a length of 1.54 angstroms. When we have ethylene, which now has, this is the sp2, that carbon-carbon double bond, the length of that bond shortens and it actually gets stronger. And then with the acetylene, which has 2 carbons with the triple bond, that gets even shorter and even stronger. So if you wanted to try to break up these molecules, you'd have to use a lot of energy to break 3 bonds versus 1 bond. And you can think of that as rubber bands. If you put rubber bands around 2 objects, that's kind of strong, but then if you keep wrapping that rubber band around more and more times, it's going to get stronger and stronger. Bond for carbon length. Single bonds are longer than double bonds, which are longer than triple bonds. The opposite is true for their strength. Triple is the strongest. And then CH bond lengths, this is for the carbon and hydrogen, follow the same trend as this up here. And the reason for the bonds being the way they are lengthwise is that sp3 hybridized orbitals have more sp. So these are the triple bond ones. It has more s character, because it's 50% S, 50% P, than sp3, which is 25% S, and that's why those bonds are shorter. The s orbitals are closer to the nucleus of atoms than p orbitals, so with triple bonds, all that electron density is held closer to the atom, which makes it shorter. Predicting molecular geometry, this is the Vesper theory. Valence shell electrons, repulsion, so that's the acronym there. Valence electrons repel each other, which we know, so they want to be away from each other as far as possible. And that repulsion causes the electron pairs to arrange themselves in 3-dimensional space, again, so they're far apart from each other as possible. We've seen something like this before. You only have to worry about a couple of molecules here in this class. You don't have to worry about super complicated ones. If it's sp3, it's tetrahedral. If it's sp2, it's trigonoplanar. If it's sp, it's linear. So I knew that there was a whole host of them when you were drawing Lewis structures in general chemistry. We only have to worry about these 3 shapes here. Within tetrahedral, you can have bent, which is 2 atoms and then 2 lone pairs. Trigonal pyramidal has 1 lone pair, and tetrahedral regular is no lone pairs. And then for trigonal planar, you have those structures in between, and then sp is just linear. So for dipole moments, electronegativity causes an induction. Induction is the shifting of electrons within the orbitals, which results in a dipole moment. And a dipole moment is the amount of charge times the distance that the partial positive and partial negative are separated. You don't have to worry about calculating dipole moments or reporting them in device, but just so you know what the units are. So a dipole moment, again, if we remember using those arrows, that just shows the direction of the electron density. So dipole moments and molecular polarity. If you have this compound here, so for our molecules with multiple polar bonds, dipole moment is the sum of all of them. So if we look at this one just individually, we have the C to Cl. You can see this is the partial negative up here, partial positive down here. And then if we have 2 chlorines, those pull the electrons in opposite directions, but it has a net dipole moment. So they're all working towards this direction. So that's the net molecular dipole moment. And if you have multiple, it just combines together. So for this nitrogen, all these electron densities going here, and then we have the lone pair. So the net dipole moment is driving upward. And then for water, you also see that same net dipole moment. If you have a carbon with 4 chlorines, those are all pulling in the opposite direction and outward from each other. So this is overall no dipole because they're pulling in different directions. So if I had a toddler pulling at each of my limbs, I am not going anywhere. So the net movement of this is neutral. So you want to consider that also when you're looking at dipole moments. In the case of here where there's 2 chlorines, those are 2 forces being pulled here. So 2 kids can pull me in one direction. 4 kids are all going to pull me in different directions. Different properties for organic compounds are based on their intermolecular forces. So things like solubility, boiling point, density, state of matter, melting point are affected by how the molecules are attracted to each other. So neutral molecules, which are polar and nonpolar, can be attracted to one another through dipole-dipole interactions, hydrogen bonding, and dispersion forces. A dipole-dipole is a force that results when polar molecules line up their opposite charges. Here we have acetone. This is the partial positive here, partial negative. So they're all molecules that have this type of dipole moment. And they're just stacking their opposite charges in a direction so that they can form that. So isobutylene does not have that polar dipole moment that acetone does. So the melting point of that one is very low compared to acetone. The boiling point is very low compared to acetone. So this is -7 almost. This is 56. So you add that extra component of dipole moment, and that's going to increase the dipole-dipole forces. So that's going to bring the physical properties boiling point higher. So you can think of this one as like magnets. So the opposite poles attract each other. The same poles will repel each other. So dipole-dipole is like the magnets. So we have large partial positive on H's that contract partial negative on other molecules. Hydrogen bonds. They are 20 times weaker than covalent bonds, but they are the strongest of the intermolecular forces, and this is definitely one that you see in DNA. This is the hydrogen bonding in DNA. Well, not all molecules can hydrogen bonds. That's only atoms with nitrogen, fluorine, or oxygen, and they have to be capable of forming these H-protic bonds. The hydrogen bond interaction between water, one H can hydrogen bond to a lone pair of oxygen on another molecule. Hydrogen bonding can occur at 4 different spots on water. So this can bond to another one, and this will bond to 2 other hydrogens here. You can see the same thing with nitrogen. You have that same hydrogen bonding here. So if you look at triethylamine, the boiling point of that is 3.5 degrees. That has one spot where it can hydrogen bond. If you add another spot of hydrogen bonding, so this nitrogen can bond to a hydrogen, this hydrogen can bond to a nitrogen. That's 2 areas. The boiling point comes to 37, and then now you have 3 areas. That's 49 degrees. Adding those extra hydrogen bonding spots will really change your boiling points and make it increase because there's more interactions there. For London dispersion, you have non-polar molecules that normally have their electrons spread out all over the place. So this here is 5 carbons bonded together. There's no dipole moment with 5 carbons. Usually it's just going to be a neutral molecule. But when they are close to each other, they can form a temporary dipole, which means they can get all of their forces together to make one negative end and one positive end. And that uneven distribution charges produces that temporary dipole, which can induce a temporary dipole to a neighboring one. So these two get all of their friends together to make one side positive, one side negative, and they can form this interaction. So this is displayed very well in a scene that I'm going to show you now.
Dory, we have to tell everybody to
swim down together! You understand what I'm saying to you? Swim down!
Everybody swim down! Come on, you have to swim down! Swim down, okay?
Down! Swim down! Swim down! Swim down! Don't give up! Keep swimming! Just keep swimming! That's it!
It's working!
Just keep swimming! Keep swimming!
Come on, Dad!
You're doing great, son!
That's my dad!
Come on, let's get to the bottom!
So you could see there, and I'll come back to the video in a second here, but all the fish were swimming in different directions, which is what you would see in a non-polar molecule. And then Nemo told all of them to swim in one direction, so he was temporarily inducing a dipole so that they could escape.
Keep swimming!
Just keep swimming. Just keep swimming.
Almost there! Keep swimming!
Okay, so as you increase the number of intermolecular forces, That also increases the London dispersion, and that will affect your physical properties. So here we have one carbon which has a boiling point of -164. As you increase the size of the molecule, your interactions, the number of interactions will also increase, and that will bring the boiling point up to 174. So increasing the size of the molecule and increasing those intermolecular reactions will increase the boiling point as well. So here we just have a difference of the dipole-dipole forces. We add a little bit of oxygen, that increases it. Here we're adding hydrogen bonds. Now we're up to 46 degrees. This can really hydrogen bond in more places, so we're up to 98. And then there's even more areas for hydrogen bonding here. Plus you have that dipole, so that really affects the boiling point. Boiling point will increase with size. So if you notice, the CH4, which is just one carbon, has a boiling point of -162 degrees Celsius, which is why methane is a gas. And as we add the number of carbons to that, the boiling point also increases. So here we have 6 carbons, and this has a boiling point of 69 degrees Celsius. So as you add carbons, that's going to add intermolecular forces, intermolecular interactions, so that's going to increase the boiling point as well. The boiling point changes with the shape of the molecule. So these all have the same formula. They all have 5 carbons, but the shape of them is different. And if you notice, the one that is this bulky shape has a boiling point of 10 degrees Celsius, whereas when it's a straight chain, it's 36 degrees Celsius. So what you're seeing is here, this is kind of a ball shape, and I'm demonstrating here as there's less surface contact with other molecules in the same bunch. So there's less dipole interactions. Here you have this flat molecule and it looks like this, so you get more stacking with the molecules, so that's a lot more interactions that can happen and a lot more of those dipole intermolecular forces, so that's why you get a higher boiling point there. In organic chemistry, when we're talking about solubility, we often say like dissolves like, so things that are similar will dissolve things that are similar. Ionic compounds are soluble in water because you get a lot of ion-dipole interactions, and water is a polar molecule. So those polar ions can interact with the polar water. Organic molecules are typically soluble in organic solvents, but not in water, so they're hydrophobic. So carbons and hydrogens are hydrophobic in nature. They don't dissolve in water very well. So oil is something that is a hydrocarbon, which is all carbons and hydrogens, and we know that that floats or is less dense than water and does not go into water very well. So organic molecules are only soluble in water if the number of carbons divided by the number of oxygens plus the number of nitrogens is less than 4. So that is something that you're going to want to remember because that will come up later. So I have 2 molecules here. This is actually a structure of soap. Soap has a polar group. This is hydrophilic, so this is the water-soluble part of the molecule, and this is a non-polar group, which is also hydrophobic. So it has these 2 ends here. And then you have this oil molecule, and oil molecules are mostly non-polar in nature, and it has a little bit of polar heads. So when you try to wash dishes and there's greasy plates, it's very hard to wash the dish because of all the oil is not going to go into the water because there are polar and non-polar. But when you add soap to the mix, the soap has this polar group that can infiltrate the polar group over here and then break up those oil spots so that you can get the dishes clean. If you have fabrics that are sensitive to water, take them to the dry cleaner, and the dry cleaners will usually use some sort of organic chemical to get your stains out. This is Propofol. You may have heard of this drug. It is normally used for initiating and maintaining anesthesia during surgery. This drug became very popular in 2009, or at least gained a lot of publicity because it was one of the drugs that were implicated in the death of Michael Jackson. This is the structure of Propofol here, and if you'll notice, there's mostly carbons and hydrogens around here, so this is mostly nonpolar. And we only have this little bit of a polar molecule here. And if you remember, for something to be soluble in water, the number of carbons over the number of oxygens and nitrogens has to be less than 4. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons to 1 oxygen. So this is certainly not soluble. So there's a lot of hydrophobic regions, which also makes it not soluble in water or blood. This dissolves in soybean oil though, so this is an oil, and also lecithin. So often it's dissolved in that and it has this milky color, and so they will often call it milk of amnesia. So this is just an interesting tidbit here. I won't be asking you questions about Propofol or the structure.